Year 13 short revision video number 20. So immediately at the start of the question we must show detailed reasoning, so really crucial that we show every step of working here. Here's the equation of a curve and we've got to find the gradient of the curve at each of the points where y equals 1. So we're looking for gradient and we're also interested in the points where y is equal to 1. So let's take this in two parts. The first thing I'm going to do is differentiate, and we've got to differentiate implicitly here. So remember, we must never write dy by dx equals, we've got to differentiate each term as it stands, going left to right. So first of all, we're differentiating y cubed, so that's going to become 3y squared dy by dx. We're then differentiating the minus xy term. So thinking about xy and how it differentiates, it's a product. So rather than writing out all of the steps of working in terms of u and v here, which can get very complex with lots of variables in the mix, I'm just going to think about the fact that we first of all leave one part of this alone, so I leave x alone. I then differentiate the other part of it, so that gives me dy by dx. I then go back to the first part and differentiate that, so that gives me a 1, and then I go back to the next bit and I leave that alone. So if I differentiate xy implicitly, I get x dy by dx plus y. Now, there's a minus in front of this, if you look here carefully. So this is going to be minus x dy by dx minus y. Now, the last part of this involves differentiating 4 root x, or 4x to the power of a half. So that's simply going to become 2x to the negative a half. Differentiate the right-hand side, which is 4, that becomes 0. Let's now collect the terms that contain dy by dx together and factorise. So that's dy by dx, and then in the bracket 3y squared minus x, and on the right hand side we'll shift everything else over, so that's y minus 2x to the negative a half. I then want to make sure I isolate, so I have dy by dx on the left hand side by itself, so that's y minus 2x to the negative a half all over 3y squared minus x. Now, I need to evaluate the gradient at each of the points where y is equal to 1. So we need to find out what happens when y equals 1. So let's go back to this equation of the curve and let's set y equal to 1. That's going to give us 1 minus x plus 4 root x equals 4. I'm going to rearrange this equation in a particular way. So x minus 4 root x plus 3 equals 0. And this is quite an interesting equation because it's actually in the format of a quadratic equation in disguise. Now, how do I sort of see that? Well, the connection is with the x and the root x. Rather than an x squared and an x, we've got an x and a root x. So why don't I say, let m squared be equal to x. And then m would be equal to the root of x. And then if I go back to this, I can replace x with m squared. I can replace root x with m, and then it becomes easier to see that quadratic format. This is an equation that can be factorised very simply. So m equals 3. Or m equals 1. Now, m, remember, is equal to the square root of x, and m squared is equal to x. So m squared equals 9, m squared equals 1. So that gives me two possible x values, x equals 9, x equals 1, both of which occur at y equals 1. Now, the last thing we need to do is evaluate the gradient at both of these points. So we need to go back to dy by dx and substitute both the x and the y values in. So dy by dx is equal to 1 minus 2 times 9 to the negative half over 3 minus 9, and that comes to a value of negative 1 over 18. And then at the other point, dy by dx is equal to 1 minus 2 over 3 minus 1, which comes to a value of negative a half.